6, then, or if they naturally exceed 6, then our computations are meaningless. Now, it's kind of curious what I might mean by exceed. It means that all of our, I don't even know how I would define it personally. The idea is that the basic computations that we do, in this case in the number theoretic transform, they initially, during the computation of the transform, we can do modular operations, but there's a point where we lose so much information that we can't do our convolutions, or we can do our convolutions, but when we do them, we can't reconstruct the original result. In other words, so the typical multiplication algorithm, maybe I should go through that. If we have our number theoretic transform, let's call that kind of fancy n. What we do is we have our input set of digits, so if we're computing 1, 2, 3 times 4, 5, 6, then we're going to have an array 1, 2, 3. Actually, we're going to have 0, 0, 0 as well over here. So this is our input number. Let's say x equals this, and then we're going to have y equal to 4, 5, 6, 0, 0, 0. These are arrays. So what we do is we compute the number theoretic transform of x. Let's call that capital X. We compute the number theoretic transform of y. Let's call that capital Y. We do the convolution, which in this sort of number theoretic frequency domain is just pointwise multiplication, so x dot y, which equals some result z. And then we do the inverse number theoretic transform of z, which gives us lowercase z, and this should equal the product of x and y. So let's suppose we're doing all these operations mod 7. Then it should be kind of obvious that our digits, for example, can't be, like let's say 462. If we have a digit that is in base, let's say 5,000 or something, and one of those digits is 462, we're going to lose that information in our modular operation here. Likewise, when we do our number theoretic transform, and if our intermediate results overflow our modulus, then we can't reconstruct the result. So for example, let's say that we had some number in an intermediate computation come up as 8. Then 8 is going to be mod to 1, and so a digit in our final results, let's say z had here this digit 8 in it, which got modded later to 1. Normally, after we do this pointwise multiplication and our inversion here, what we're supposed to do is get our result back, let's say 5, 21, 4, 3, something, blah, blah, blah. What we're supposed to do is start propagating carries. So in this case, 3 is less than 7, that is nothing to propagate. 4 is less than 7, nothing to propagate. 21 is greater than 7, so we have to propagate the difference there, and so this will add. So what is it? So that's what would happen. However, if we're modding by 7, let me use a smaller example. Let's actually do a propagation. I'll use my intermediate result 8 here. So let's suppose we had 4, 8, 2, 1. There's only one thing no carry to propagate here, so that's good. No carry to propagate here, that's good. We have a carry to propagate here. So this result boils down to 1. And since let's say our base is 7, then we propagate 1 up here, so this turns into 5. 5 is okay, so our final result is 5, 1, 2, 1 here. So we need our carries to be propagatable. And so the issue then is if we start modding things by 7, for example, and our number exceeds 7, then before we can even propagate the carry, this is going to get turned into a 1. So it's our final result coming out of the array, or coming out of the inverse transform, is going to be 1, 2, 1. But before it even propagated, we have our number 4 here. So when we go through and propagate, it's going to be 2, or 1, yep, that propagates. 2, yep, that's fine. 1, that's fine. 4, 1, and we see that we have the wrong result. We needed 5, 1, 2, 1, not 4, 1, 2, 1. This is a problem when, especially when our base B, well, it's not a problem with this, but you observe it more easily when our base B is less than our modulus M. This is almost always going to be the case, our base less than our modulus. If our base was 10, for example, and our modulus was, or if our base was 5 and our modulus was 7, then we can propagate all carries that are greater than 5 here. But if they ever exceeded 7, then they'd be reduced and we'd lose that information. That was a little bit of a clunky explanation to this, but the point is that our final calculations in our number theoretic transform need to be bounded in some sense. So the question is, what is the maximum representable number that we need within our number theoretic transform? Or what maximum does the number theoretic transform provide when we go through all the calculations? So if we have some maximum, which turns out to be, let's say, M, then we know that our modulus, I shouldn't have used M there. Let's say our maximum is A. Then we know our maximum, our modulus must be greater than A. So we never get any overflow. So as long as this situation is okay, then we got it. But we need to figure out what A is. So let's clear this out. And let's look at the number theoretic transform in a little bit of a different lens. I don't know if there's a good way to clear this fast, but I don't really know this software. No. Also, why don't we change the color here to a nice orange. So one other way to look at the Fourier, so Fourier transforms are linear operators, and as such in some space we can represent it by the typical representation of a linear operator, namely a matrix. I mean, this is a finite, it's working on a discrete number of elements, so we can represent it as a matrix. This matrix is called the Fourier matrix, Fourier matrix. And this matrix is equal to, it's like a big matrix of primitive roots. We have omega 0, omega 0, omega 0, omega 0. In the first column, likewise the first row is omega 0, omega 0, omega 0. And then we kind of, the second row is increasing by 1, so this would be omega 1, omega 2, omega, this would also be, what is this? Let's see, omega 0, 1, 2, oh yeah, this would be omega n minus 1. This would be omega 2, because we go rows and columns. So this is a symmetric matrix, symmetric. Omega n minus 1. So this one we're going up by 0, up by 1, up by 2 each time. So this would be omega 4 dot 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 omega 2 n minus 1. Likewise, we'd have omega 2 n minus 1 here because of the symmetric property. So we're going up by 0 here, up by 1 each step, up by 2 each step. The next one would be up by 3, dot dot dot. Next one up here is up by n minus 1. You can see we have 0, n minus 1, 2, n minus 1. And so the very, very last element in the bottom right-hand side of the matrix would be n minus 1 squared. So in essence, we can say that if this matrix right here, if we look at our input as a column vector, so this is a column vector right here, col vector, and this is another column vector, col, and let's call this matrix the Fourier matrix. Let's use like some fancy f. Then our Fourier transform is thus represented, or our result is written as this. So our Fourier transformed result, fi equals our Fourier matrix times lowercase fi. So we have a matrix representation of the sum, and it's relatively easy to check that this matrix right here, this matrix multiplication by the vector is the same thing as this sum property. Before I want to check something. Okay, good. Now what I'm going to do is, so I'm going to say, I'm going to rewrite this thing up here. F, capital F, equals our fancy Fourier matrix times lowercase f. So writing out the column vectors now. Whoops, I made that line on accident. If we write out the column vectors, this would equal f0, f1, this pen is weird, dot n minus 1, and over here obviously we write our lowercase versions, f0, f1, dot dot dot, f n minus 1. So what we do is we want to make a bound. Now assume this Fourier matrix is in our set mod M. So let's erase again. Let's erase some of this stuff. Let's say that our modulus is lowercase m. So I'll write that up here. Our modulus is lowercase m. Then what that means is that all of our primitive roots are going to be between 0 is less than or equal to our omega to the power of, it doesn't matter what it is, I'll just say j, which is less than or equal to m. Because we're working in that equivalence class. So all of these elements of this matrix are between 0 and m exclusive of the upper bound. And if we look at just one of these products, let's look at what f is. Again, as evident from the sum, what this is going to be is this. Let me use a different color now because I'm starting to mix them. This is going to be this. I actually just chose like literally the exact same color. It's going to be w times f, or omega 0 times f, omega 0 times f1, blah blah blah, and that's going to be the first one. We get that sum. So for our first element, we're adding together how many elements of omega, how many elements of this field. There's going to be a total of n, because the width of this matrix is n. So we know that our first element, f0, If all elements are